Hello, and today we're going to look at a term, a physics term, latent heat. Let's pop up the definition. I have this graph on here because we're going to refer back to this in just 1 second, in a moment here, but let's pop over here. So let's look at latent heat. The heat energy involved in a change of state is called latent heat. So change of state. What does that mean? Change of state. Ooh, we don't want to go with this. Change of state means, oh, I better change this over here. Yikes. Change of state refers to, I'll just talk while I'm changing here. Change of state refers to a substance changing from a solid to a liquid, or a liquid to a gas, or of course the opposite, going from a gas to a liquid, or a liquid to a solid. Now, is this going to work? Yes, it is. Is it going to work? Sorry about that, guys and girls. There we go. Okay, yeah. So the heat energy involved in a change of state. The quantity of heat involved depends not only on the latent heat, and this is a constant, we'll look at this in 1 second, but also on the mass of the substance. So obviously the bigger or smaller an object is will have an effect on how fast or slow it changes states. We have a formula here, and we looked at this formula previously in some of my problems, MC delta T, and I don't want to spend a whole lot of time on this. We have our Q is our heat energy, mass is our mass is our substance, yes. C is our object, and it's a constant. And we have this guy right here, change in temperature. Well, I just want to say, when we're talking about using latent heat and using a reference to a latent heat formula, we aren't going to have a change in temperature, because what we're looking at is a change of state, and when something changes states, when the process begins, there is no temperature change until the process finishes. So let's flip over to this slide. Oh, yeah, thank you. And we have something that looks like this. Now, this is water, and we know that water freezes or melts at 0 degrees Celsius, right here. And we also know that it boils or condenses at 100 degrees Celsius. Now, we have 5 little situations here, 5 little scenarios. We have ice, solid, so I'm just going to label a graph. If you've got something at -20 up to 0, then if the substance is water, that's ice. Now right here, guys, right there, okay, that's B, and that is when you have a change of state occurring. Okay, and a change of state here, we're going to do some problems. I'm just going to move this over here, and when we determine mathematically how much heat energy is involved in that change of state, we're going to look at using this physics formula. We've seen this guy before. Q is our heat energy measured in joules. Mass is our substance measured in either grams or kilograms. And this is a new term, latent heat of fusion. And that's our constant. And with water, ice, steam, our latent heat of fusion, when something is changing states, either if it's giving off energy or gaining energy, right? If you're talking about water, if you're talking about ice changing states to form water, then we have it gaining 300. In order for that to happen, it's going to have to gain 333 joules per gram. So for every gram that you have, there's going to have to be 333 joules of energy added to that substance in order for it to melt. On the flip side, if it is going in this direction and it is melting, it's going to have to give that energy off in order for it to form ice. Okay? Now, we have water, liquid, and that's C. And we have water that's going to go from 0 And there's lots of questions and problems that we can use that would involve lots of delta T's. Formula would look like this. Q equals MC delta T from here to here with C. Okay, but at D, where this thing changes states again from water, right? Here it is at C, water, to vapor or steam. Your formula, I'm just going to put this down like this. Your formula is going to look like this. Q is equal to MLV. Quite similar to our MLF down here. The Q is the same. It's your heat energy measured in joules. Your mass is the same. It's the mass of the substance that you're looking at. In this case, we're looking at water. We'll look at some different substances and some problems here shortly. Your LV is your latent heat of vaporization, and that is the amount of heat energy required to change water, in this case, into steam. And this is a constant. And this constant is 2,000, a little more energy involved here, 2,260 joules per grams. And notice there's no degrees Celsius. When we were looking at this constant earlier in some of our other problems, for instance, water, it was 4.18 joules over grams degrees Celsius. And the reason the degrees Celsius was there was because this type of a problem involved a temperature change, which of course was consistent with your constant, which had a degree Celsius there. In your change of states, in your latent heat scenarios, there is no, do you notice in your constant, it's joules over grams here, joules over grams there, because when it's changing states, let's say from ice to water, there is no change in temperature until the process is finished. This is in a perfect situation, a closed situation. And the same up here, look, when water is changing into water vapor or gas, right? Gaseous vapor, there is no change in temperature until, of course, the process finishes. Okay, I'm just going to flip back to the slide and some nice definitions here you can look at. There's your latent heat of fusion, joules over grams. I talked to you about that. Mass is can be represented as either grams or kilograms. Q is your heat transferred in joules. LF is the energy required to melt 1 gram of a substance to form a liquid, or the quantity of heat given off when 1 gram of a liquid changes to a solid. We talked about that. LV, same idea, except you're talking about water changing to a gas. And of course, if you're going the other way, from a gas to a liquid, it's the amount of energy is going to be given off or released. And there's your formula for vapor, and here, where is it? Here is your here is your formula for water changing to ice, or ice melting to water. We're going to look at some problems here shortly, but I just wanted to show you, or just give you a general idea of what's happening here in terms of substances changing states. Okay, and we're going to use the term latent heat. We're going to use latent heat with different substances shortly. Okay, so I hope this helped. Thank you, and have a great day, and keep checking back on my site, and we're going to be looking at some latent heat problems here shortly. Thank you.